that we're done answering the Chapter 5 activities and the packet tracer activities, we can now proceed in the summary for the whole chapter. So Chapter 5 is all about Ethernet. So Ethernet is now the predominant LAN technology in the world. Ethernet operates in the data link layer and the physical layer. The Ethernet protocol standards define many aspects of network communication including frame format, frame size, timing, and encoding. When messages are sent between hosts on an Ethernet network, the host format the messages into the frame layout that is specified by the standards. This chapter examines the characteristics and the operation of Ethernet as it has evolved from a shared media, contention-based data communications technology to today's high bandwidth and full duplex technology. So Ethernet encapsulation. Ethernet operates in the data link layer and the physical layer. It is a family of networking technologies that are defined in the IEEE 802.2 and 802.3 standards. Ethernet supports data bandwidths of 10 MB per second, 100 MB per second, 1000 MB per second, 10,000 MB per second, 40,000 MB per second, and 100,000 MB per second. LLC sublayer. The Ethernet LLC sublayer handles the communication between the upper layers and the lower layers. This is typically between the networking software and the device hardware. The LLC sublayer takes the network protocol data, which is typically an IPv4 packet, and adds control information to help deliver the packet to the destination node. The LLC is used to communicate with the upper layers of the applications and transition the packet to the lower layers for delivery. MAC sublayer. MAC constitutes the lower sublayer of the data link layer. MAC is implemented by hardware, typically in the computer NIC. The specifics are listed in the IEEE 802.3 standards. Data encapsulation. Process includes frame assembly before transmission and frame disassembly upon reception of a frame. In forming the frame, the MAC layer adds a header and trailer to the network layer PDU. Data encapsulation provides three primary functions. Number 1 is frame delimiting. The framing process provides important delimiters that are used to identify a group of bits that make up a frame. These delimiting bits provides synchronization between the transmitting and receiving nodes. Number 2 is addressing. The encapsulation process contains the layer 3 PDU and also provides for data link layer addressing. And the last one is the error detection. Each frame contains a trailer used to detect any errors in transmissions. Media access control. The second responsibility of the MAC sublayer is media access control. It is responsible for placement of frames on the media and the removal of frames from the media. As its name implies, it controls access to the media. This sublayer communicates directly with the physical layer. Ethernet frame fields. The minimum Ethernet frame size is 64 bytes and the maximum is 1518 bytes. This includes all bytes from the destination MAC address field through the frame check sequence or the FCS field. The preamble field is not included when describing the size of a frame. MAC address and hexadecimal. An Ethernet MAC address is a 48-bit binary value expressed as 12 hexadecimal digits or 4 bits per hexadecimal digit. Just as decimal is a base 10 number system, hexadecimal is a base 16 system. The base 16 number system uses the number 0 to 9 and numbers A to F. It is easier to express a value as a single hexadecimal digit than as 4 binary bits. MAC address and hexadecimal. Given that 8 bits or 1 byte is a common binary grouping, binary 000000 to 111111 can be represented in hexadecimal as the range 00 to FF. Leading zeros are always displayed to complete the 8-bit representation. For example, the binary value 000 and 1010 is shown in hexadecimal as 0A. Note that it is important to distinguish hexadecimal values from decimal values regarding the characters 0 to 9. Representing hexadecimal values. Hexadecimal is usually represented in text by the value preceded by 0x. For example, 0 times 73 or a subscript 16. Less commonly, it may be followed by an H, for example 73H. However, because subscript text is not recognized in command line or programming environments, the technical representation of hexadecimal is preceded with 0x. Therefore, the samples above would be shown as 0x, 0a, and 0x73 respectively. Hexadecimal is used to represent Ethernet MAC address and IP version 6 addresses. Hexadecimal conversion. Number conversions between decimal and hexadecimal values are straightforward. But quickly dividing or multiplying by 16 is not always convenient. If such conversions are required, it is usually easier to convert the decimal or hexadecimal value to binary and then convert the binary value to either decimal or hexadecimal as appropriate. MAC address, Ethernet identity. In Ethernet, every network device is connected to the same shared media. Ethernet was once predominantly a half-duplex topology using a multi-access bus or later Ethernet hubs. This meant that all nodes would receive every frame transmitted. To prevent the excessive overhead involved in the processing of every frame, MAC addresses were created to identify the actual source and destination. MAC addressing provides a method for device identification at the lower level of the OSI model. Unicast MAC address. A unicast MAC address is the unique address used when a frame is sent from a single transmitting device to a single destination device. The process that a source host uses to determine the destination MAC address is known as Address Resolution Protocol or the ARP. ARP is discussed later in this chapter. Although the destination MAC address can be a unicast, broadcast, or multicast address, the source MAC address must always be a unicast. Broadcast MAC address. A broadcast packet contains a destination IPv4 address that has all ones in the host portion. This numbering in the address means that all hosts on the local network or the broadcast main will receive and process the packet. Many network protocols such as DHCP and ARP use broadcasts. Multicast MAC address. Multicast MAC addresses allow a source device to send a packet to a group of devices. Devices that belong to a multicast group are assigned a multicast group IP address. The range of IPv4 multicast addresses is 224.00.0.0.02 239.255.255.255. The range of IPv6 multicast addresses begin with FF00 /8 because multicast addresses represent a group of addresses sometimes called a host group. They can only be used as the destination of a packet. The source will always be a unicast address. Switch fundamentals. A layer 2 Ethernet switch uses MAC addresses to make forwarding decisions. It is completely unaware of the protocol being carried in the data portion of the frame, such as an IPv4 packet. The switch makes its forwarding decisions based only on the layer 2 Ethernet MAC addresses. Unlike legacy Ethernet hubs that repeat bits out all ports except the incoming port, an Ethernet switch consults a MAC address table to make a forwarding decisions for each frame. The 4-port switch was just powered on. It has not yet learned the MAC address for the 4th attached pieces. Filtering frames. As a switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. When the switch MAC address table contains the destination MAC address, it is able to filter the frame and forward out a single port. Cut-through switching. In cut-through switching, the switch acts upon the data as soon as it is received. Even if the transmission is not complete, the switch buffers just enough of the frame to read the destination MAC address so that it can be determined to which port to forward the data. The destination MAC address is located in the first 6 bytes of the frame following the preamble. The switch looks up the destination MAC address in its switching table, determines the outgoing interface port, and forwards the frame into its destination through the designated switch port. The switch does not perform any error checking on the frame. So there are 2 variants of cut-through switching. First one is the fast forward switching. So it offers the lowest level of latency. Fast forward switching immediately forwards a packet after reading the destination address, because fast forward switching starts forwarding before the entire packet has been received. So there may be times when packets are relayed with errors. The next one is the fragment free switching. So the switch stores the first 64 bytes of the frame before forwarding. It can be viewed as a compromise between store and forward switching and fast forward switching. The reason fragment-free switching stores only the first 64 bytes of the frame is that because most network errors and collisions occur during the first 64 bytes. Memory buffering on switches. So port-based memory buffering. In port-based memory buffering, frames are stored in queues that are linked to specific incoming and outgoing ports. A frame is transmitted to the outgoing port only when all the frames ahead of it in the queue have been successfully transmitted. It is possible for a single frame to delay the transmission of all the frames in memory because of a busy destination port. This delay occurs even if the other frames could be transmitted to open destination ports. Shared memory buffering deposits all frames into a common memory buffer that all ports on a switch share. The amount of buffer memory required by a port is dynamically allocated. The frames in the buffer are linked dynamically to the destination port. So this allows the packet to be received on one port and then transmitted on another port without moving it a different queue. Duplex and speed settings. So there are two types of duplex settings used for communication on an Ethernet network. So full duplex, so it has both ends of the connection can send and receive simultaneously, and the half duplex is only one end of the connection can send at a time. Auto MDIX. When the Auto MDIX feature is enabled, the switch detects the type of cable attached to the port and configures the interfaces accordingly. Therefore, you can use either a crossover or a straight-through cable for connections to copper 10/100/1000 port on the switch, regardless of the type of device on the other end of the connection. Destination on the same network. So there are two primary addresses assigned to a device on an Ethernet LAN. Physical address or the MAC address, used for Ethernet NIC, two Ethernet NIC communications on the same network. Next is the logical address or the IP address. It is used to send the packet from the original source to the final destination. Destination on the same network. The layer 2 Ethernet frame contains destination MAC address, so this is the MAC address of the file server's Ethernet NIC. Next is the source MAC address. So this is the MAC address of PCA's Ethernet NIC. The layer 3 IP packet contains source IP address. So this is the IP address of the original source PCA. And the next is the destination IP address. So this is the IP address of the final destination, the file server. Destination remote network. When the destination IP address is on a remote network, the destination MAC address will be the address of the host's default gateway, the router's NIC, as shown in the figure. Using a postal analogy, this would be similar to a person taking a letter to their local post office. All they need to do is take the letter to the post office, and then it becomes the responsibility of the post office to forward the letter on towards its final destinations. Introduction to ARP. So recall that every device with an IP address on an Ethernet network also has an Ethernet MAC address. When a device sends an Ethernet frame, it contains these two addresses: the destination MAC address and the source MAC address. So the destination MAC address is the MAC address of the Ethernet NIC, which will be either the MAC address of the final destination device or the router. And the source MAC address is the MAC address of the sender's Ethernet NIC. Resolving IPv4 addresses to MAC addresses. When a packet is sent to the data link layer to be encapsulated into an Ethernet frame, the device refers to a table in its memory to find the MAC address that is mapped to IPv4 address. This table is called the ARP table or the ARP cache. The ARP table is stored in the RAM of the device. So if the packet's destination IPv4 address is on the same network as the source IPv4 address, the device will search the ARP table for the destination IPv4 address. If the destination IPv4 address is on a different network than the source IPv4 address, the device will search the ARP table for the IPv4 address of the default gateway. Removing entries from an ARP table. Commands may be used to manually remove all or some of the entries in the ARP table. After an entry has been removed, the process for sending an ARP request and receiving an ARP reply must occur again to enter the map in the ARP table. ARP broadcasts. So ARP broadcast frame is an ARP request is received and processed by every device on the local network. On a typical business network, These broadcasts would probably have minimal impact on network performance. And next one is the ARP spoofing. Excuse me. The use of ARP can lead to potential security risk known as ARP spoofing or ARP poisoning. This is a technique used by an attacker to reply to an ARP request for an IPv4 address belonging to another device, such as the default gateway. The attacker sends an ARP reply with its own MAC address. The receiver of the ARP reply will add the wrong MAC address to its ARP table and send these packets to the attacker. So that's the end of chapter 5 summary, and I hope you learned something from this video. Thank you for watching, guys. Bye!